Good morning. Am I? Good morning. Am I audible now? My voice is okay?
Yes, sir.
So good morning. I think let's get started. So we are trying to look at various aspects of controllers. Okay. Also, specifically speaking, feedback controllers, and we have seen uh, some examples in this how this is being really implemented. And I also kind of requested you to kind of go back and check how a control room works, how if you could check, if you could see some videos and things like that, how really this is applied in industry. You would have a control room wherein people would be sitting and entering set points, control, tune, what you call the values of the controller, parameters, everything through a distributed control system, or sometimes it may be locally. So sometimes it may be locally connected. Give me a minute. Yes. So this is what. So sometimes the controllers are either implemented at local locations. Okay, so then in that case, it is a hardwired control. Basically, then it's what you are going to fix is the circuit, electronic circuit. You work all such calculations. See, every mathematical calculation can be, for instance, sum of addition, multiplication, integration. Everything can be realized by means of electronic circuit. You only need to kind of arrange them properly by means of resistance, capacitance, inductance, their parallel or series combination, all the numerical calculations, for instance, addition, multiplication, could be realized. So, so basically, what are we doing? So we are just implementing a rule in a controller. For instance, if error is more, you take action. If error is less, you take another action. So all this could be typically kind of implemented by means of uh, electronic circuit. So then it is a hardwired controller. Okay, so then the difficulty that you would have is the maintenance of the same, because it's a device, right? So over the time, for instance, the resistance or maybe the capacitance, what you call that you have installed, okay, or rather that you got as part of the overall controller board that you when you purchased, this quality goes down. So you would see that hardware controller will not last long, like any electronic equipment. So so the long things would kind of their performance would degrade with respect to time. But but like soft controllers, which is basically a control algorithm, right? So hardwired controller. So someone can even go and buy, if you go to an electronic shop, okay, not a typical electronic shop where they sell in what you call uh, electrical devices. You can buy. P controller, PI controller, PID controller, etc. What you call as a package. So most likely it would be a PID control. We have not learned what is PID controller. We will see. Most likely it would be a PID controller. And if you need to activate P in that, you will have to switch off. It's like regulator, right? So you see fans regulator, wherein you change the speed from 1 to 5 by turning a knob. So in the same way, you can actually get this connected. Huh? So what I am trying to say is that is one way if you wanted to do it in a hardware fashion. So in a software way, so what you would do is you take this control algorithm K times ET. If it is if it is if it is proportional controller, and we also seen something known as integral controller, 1 by tau I times integral of ET dt. So all these terms, so this I will take the term corresponding to the proportional term. This is the integral term. So you would see 3 knobs. So you would it might be a bit more clearer when you do possibly the process control lab next time. So you would see no, I think there is one device that is having hardware controller, rest are all software controller. So it would be written P, it would be there would be PID3. So what you would see on the top circuit would be of course inside. It would be nicely wrapped up, and you would get a so inside this box. So it would be a box, maybe a thick, and maybe look like a slice of bread. You see. So what you would see on the top would be some knobs, maybe written Pi and some range of values, integral for a range of values, derivative for a range of values. And of course, on inside, they would have implemented the circuit. And you can have this, the range of values, of course, as I told, this would be most likely in knob, okay? And you would have a needle or something, some sort of that would be here, and you would change it. So this may be 0, and you would have a maximum minimum capacity based on the hardware elements that they have used inside the circuit. So it could be 0. Now 0 essentially means that component, that particular component is not part of the uh, uh, so that component is not part of the overall control scheme. So if you select, if the knob is 0 for proportional, then there is no proportional action. The same applies for integral and derivative. So you will not be able to buy these P, I, and D separately. What you get is an integrated device. You switch off or switch on. Like a similar example that you would see is like a regulator. Very, very similar. Okay. Okay. So this is for but the problem here is maintenance. A lot. Why? Any question? Somebody. Okay. So why? Because first of all, this is placed in field, and it would be susceptible to high temperature, pressure, temperature, whatever. Then also what you call rapidly changing ambient conditions. Sometimes it is affected by, so see all of these are sensors, so not sensors, electronic equipment, electronic devices. Like for instance, you would have a resistance, a capacitance, and you would kind of arrange them series parallel and do some, and there would be so this would be connected to an electronic source. So of course there would be a power source in which this would be connected. So you would see that it is connected. Sometimes there would be a ground also. So eventually it takes the power, it activates some part of the based on the what you call tuning or relationship that you have taken, it would kind of either partially activate a path or not. So based on that, you would eventually get the control, because eventually what you are sending in. So let's assume this is a board, controller board. Okay. So out of the controller board, what you really need 4 to 20 milliampere, which is the for 1 to 5 volt. This may be good enough. This may be good enough to drive your. This may be good enough to drive your I to P and followed by control valve. So most often you would supply, you would give this to supply, not of course not 230 volt. So there would be somewhere a 230 volt, there would be stepping down, and at max you would send a 10 volt signal to the controller board just to power it up. And the resistance and the capacitance which is series in parallel and corresponding to whatever be the amperage. And you would get the output voltage either in terms of 1 to 5 or in terms of 4 to 20 milliampere, because you would also supply current, right? So it's basically, what are you doing? You're just supplying a, so you're doing a control. You're basically doing an like current regulation, right? Or voltage regulation. So this is the same case. This is very, so that's why I told this is very similar to the concept, similar to what you see as in a regulator of a fan. Okay, you send in full 230 volts, there are various resistance, and there are, so you would see if none of them are channelized, you would get the full voltage. Let's say at least one channelized, you might be getting, your speed would be reduced by that much amount of the corresponding voltage drop. The same applies in all of it. So coming back to the stress that these hardwares would see in the field is of course high temperature and pressure, and a tropical country would have of course issues related to wetting, rain, humidity. This is two big things because these are all detrimental to any electronic circuit. And let's say if you're going to countries, for instance, which are closer to the far away from the equator. So then the issue would have been winters, because their temperatures are fairly low during the night time or during close to winter. Probably Northern America and Europe would start, now itself they would have started cooling. So this ambient condition could also play a role in influencing, because as I told, these are all electronic circuits. So if you don't have any way, you go and keep it installed. But otherwise, as I told, you could take the wiring either by means of a smart sensor which can send the signals, or you can wire it up to the central control room where you do this calculation by means of a computer. So what it generally says, so your computer would, so you, let's say you got the error, so you will get the signal of the measurement element, so ym, and you know the, so again in terms of whatever 4 to 20 milliamps or something like that, and you will have the reference set point in terms of 4 to 20 milliamps, and that would be your error. Okay, and all your controller output P is proportional to the error that your DCS would calculate. And what it has to do, it has to just, so then what you only need a voltage or current source. Okay, so you would have a current source or possibly a voltage or bar current source. Okay, and the DCS would trigger a signal. Okay, so just output, let's say 4 milliampere current from this source, then that would be going to the ITP. Based on this error, your controller output, basically your DCS calculates. Now this controller output, if let's say gives you 20 milliamps, which is the other extreme, the DCS would trigger a signal. Okay, gives so the source should give an output corresponding to 20 milliamps. So this is the way it is finally implemented in field. So don't think that this is an easy exercise. Okay, that's why I went into every detail and explained it. So this is so most often. So this is done by in the field events of electrical. So you require multiple people to do it really in the field. Of course, electrical engineers who would play, or sometimes instrumentation engineers, so that they will all another group of people would be able to do this. Of course, that chemical engineers. We are inevitable to explain the logic. While the circuit, sometimes in many of the industries, even chemical engineers are capable of doing this, because over the time you have changed the role. But eventually, it is a mix of these two groups would what you call do would involved in doing this. Now coming to where we have stopped. So we have seen about a proportional controller, and we will see something. We will now see about the other aspects of two types of controllers. So proportional. So we have seen to some extent it is basically K times E plus P bar will be P. So P bar, sorry, let me put here P. P bar is what is the bias signal, which is good enough to activate the overall circuit, and K times C. Now comes integral. We have started the discussion on the integral term. So integral control will also have bias P is equal to P. So always everything is P of T. Yeah? And let me put it P of T. P bar plus 1 by tau I, which generally called as integral time. So what is the key difference here? So there it was, so the output is not based on, so here the output is based on a point error. You calculate the error real time, and the output is controller output is directly proportional to that. While here it is historical summation. Historical errors are accounted. So you are integrating the error from certain time to certain time. So as a result, it is so once an error is accumulated, you won't see it disappearing, right? As a result, what would happen is integral action, if you activate, okay, will be forever. So that's why I think in the last class I told it's like a guard, because this error is never going to be zero at some point, because whenever you see an error, that is all going to the summation, right? So let's say this is the, and this is your set point. This is where you need to reach. And this is yt, and with respect to time. So these are all, and finally consider a second order kind of a dynamics, eventually kind of controlled by means of a controller. So this is an error, this is error, this is maybe, let's assume some convention. So let's say this is positive and this is negative. So this is positive, this is negative, this is positive, negative. So you would see that whenever you do this whole summation, there would be some residual error remaining. So your control action being K times integral of E of t dt. So this term, so of course some part of which cancels out, and and it should also be, because you should not have large amount of integral action whenever you are close to your set point. Initially, yes, because you need to so it's like applying the accelerator, right? So when you apply axle, so you need to have, let's say you are interested in driving the vehicle at 140 is too much, let's say 100 kilometers per hour, and you are starting of course from a traffic signal which may be 0 km/h. So you would just press it. So initially you would go up, okay, and sometimes you might have pressed so high, so the speed went more than 140 km/h, then come down, then eventually the overall summation of the error would be very close to zero. Like, could be close to zero, but never be zero. Okay. So there would be always an integral action. So as a result, when you apply integral action, so you will see that there won't be any offset. There will not be any offset. So offset is what? This is variation from the set point, right? Your controller action cannot be off, right? So your integral action keep on supplying errors, keep on supplying the control action, even if it is close to zero. So as a result, there won't be any offset. So, but you would eventually, but this would eventually manifest in terms of oscillation. So there won't be any offset, but there might be oscillation. So what you would really see that, okay, so if this is the set point and based on only an integral action, okay, so your errors would keep on decreasing. So could you see my screen? Hello? Hello?
Yes, sir.
Could you see my screen? Am I
Yes,
audible?
yes, sir. You're audible.
Okay. So as a result, you would not reach this set point in 100%. Yeah. So you will not be able to eliminate the set. So you will not be able to kind of lie very close to the set point. What you would really see, there would be some oscillations like this. Because the error, and when you take the average of this would be your set point. So integral action is always active, right? So integral action is always active. As a result, there would be some level of control action. So there won't be any offset. So offset is something like this. So this is oscillation. While the offset is something like this. Okay, so you have a set point and finally your system operates like this. So this is set point and this is your YM finally. Here this is set point and this is your YM. So here this is a clear offset, which essentially means that your output is not coming back to the desired position. While here it is coming back, okay, but eventually, so by saving from oscillation, by saving from offset, this has eventually resulted in some level of oscillation. But that the oscillation would keep on decreasing. So that's why this integral time value, tau I, is an important term. If you don't choose it wisely, right, this effect of this integral term would be very high. So sometimes if the integral action is very high, you won't, of course there won't be any offset, but eventually it results in some sustained oscillations towards the end, which is technically again not desirable. Why? Because see, if sometimes you may be satisfied by the original variable. So for instance, let's say this variable is temperature. So this it may be okay for you to have a variability in the temperature like this, but let's say, but this is affected through again our control valve, right? So control valve keep on oscillating because this finally the output of the controller is going to control valve via I to P. So what would happen is your stem keep on moving up and down, up and down, up and down. Diaphragm keep on shrinking up and down, up and down, up and down. As a result, very soon you will have to kind of replace it. High maintenance cost. So you will have to be very careful about designing a control because there are various hardware elements involved, and there is cost associated with it. And so you see, In any way, you may have to change your control valve in maybe every 12 months or so, which you would have you have budgeted. But by doing improper controller tuning, you might eventually kind of change the control valve in every week. Okay, then that is like a bad strategy. So somebody, if you own an industry, you never like to have such a thing. So let me see if I left some point. This is what I told. Eventually, the errors will not be zeros. So there may be some residual error that would be always there that would be driving the controller output. So you would see that integral action eliminates the offset at the cost of oscillation, which could be made mild, okay, if you tune the controller properly. But if you are doing a poor tuning, then it's like as bad as the experience as an offset. You would keep on oscillating. This is of no use. Either your final control element will go back, which is your control valve, or even what you call your final product specification can go. Okay, so now coming to so eventually, see, we will have to implement everything via. So see, our model is in terms of transfer function, correct? So we have learned P controller corresponding transfer function, which is controller. Okay, let's say. Another thing which is there in the loop, which is you will also have a transfer function corresponding to that. So what our intention would be to calculate the overall response, which is this ym what I have shown by means. So let's say output by input, which is like G process. This is like an overall transfer function. So overall transfer function in a system, in an operation, in a control loop would include, okay. So let's see how it works. Okay, so you have, this is your process. This can be your stir tank, water, whatever maybe. It's generally represented by GP of us. We have our first part of the course was fully about developing transfer functions for this. Correct. So we have learned various ways to develop this transfer function. And just before your GP, what is there is your final control element. So I will say that it is V. V stands for valve. It should also be in terms of what you call transfer function. Okay, and just before that, that should be your controller. Assuming I to P converse, so assuming that I to P has a unity transfer function. Let's, if you want to do everything, let us draw. So I think that's always better. So let's say, so I'll move GP over here. This is GP of S. Okay, just before that you have GV, which is GV of S. Just before that you have, let's say so GI to P of S. You would have a transfer function corresponding to that also. So then you would have G controller of S, GC of S. And what is the input to the controller is the error. So you would supply here set point. Fine. And this is your output. Final process would be your Y output, which I will say as Ym. And this Ym is generally measured by means of a what you call sensor. So I'll say GS of it. Okay. And this sensor output is actually the measured output. Ym, whatever be the Ym which is coming out of the processor, you have only access to the measured value. So let's say your original temperature is 100, okay, and but your sensor measure as 90. You only have the value of 90. You don't know which is 100 or what. So your accuracy of the sensor is a key thing. Many of the time, people would install multiple sensors, take averages, many ways. So we are not going to the instrumentation aspect of it, but assume that your sensor is able to measure the variable very accurately. And that kind of centered. So this thing is called comparator. So the set point plus the sensor output would be computed as an error, and this error is going to the controller. Controller would contact to the I2P, which most likely assume that there is no scaling, so you could assume that to be unity, and there would be control valve. So I'll just put them in a block. So sometimes they may act together. So you can put a common transfer function for all of this. Finally, the process. So now what I am trying to say is we are interested in finding the transfer functions of each of this so that we can calculate. So we can calculate the output as a function of input. So which is y m by, or in fact y by u, some transfer function, which is overall in the loop. So your loop contains such various elements. So in that spirit, so we have learned the transfer function of the P controller. Let's say you're installing PI controller, you also need to know the transfer function of PI controller. So again, so your equation is what? P of t is equal to P bar times integral E of t and by tau I, of course, dt. So in terms of deviation variable, of course, this would be P prime t, okay, 1 by tau I integral E of t dt. So taking the Laplace on both the sides, it would be P prime s, okay. So it would be 1 by tau I s E of s ds. And this would come over here. So P of s by E of s would be 1 by tau I s. So this is the this term. Okay, so now let me also say since P, so people solve incremental development, right? So there is some advantage of P and some advantage of I. So what is the advantage of P and I? So P is instantaneous. Output is P of t is P bar times K into Et. So this is if the error, so when you, the error at the starting point would be very, very large. So for instance, it is y set point minus ym, right? So when you start from a very far away value of ysp, the error would be very large. So integral action, initial integral action would be very, so this is the proportional term. So initial proportional effect would be very high, initial effect. Why? Because it is directly proportional to the error. While I is proportional to the integral of the error. So which is a slightly slow thing, right? So integral will accumulate over time. But so this is initially less, but long term better, because your errors will not go zero. Initially, in the sense, you will have to calculate the integral. So immediate effect will not be there. So you will have to do the computation, then only the integral error comes. So people now thought, okay, can we combine these two things together? So you have an initial push followed by the integral action that would eliminate the offset. So that kind of gives rise to what is known as PI, or proportional integral controller. So the output would be, okay, K times Et, again K times integral 1 by tau I times integral of Et dt. So plus, of course, a bias. This is your P of t. So you have a proportional action, and this is the integral action. So, so because these are all additive, right? So if there is an initial proportional effect, that would also sum down. Okay, so then you can even calculate the overall transfer function here, P of s, which would be K C plus 1 by tau I times S into E of s. which is the transfer function of PI controller. This is what it is written over here. Okay, so this is what proportional integral controller do. So because of the integral action, right? So your initial effect is very high. So then it is the errors effect into the what you call integral term. So when you start itself, you are getting a push to integration. So you are getting double advantage. But again, so there are two things. This integral action, as I pointed out, what would happen eventually would be you might reach the set point. So there won't be any offset though. So let's say this is your set point ym. This is ysp and ym of t over time. You would see there's some oscillation which might give me. So the error will go, offset will be 0. But when I say this is what some word I have used last time, asymptotically. Asymptotically means that whenever, so it's like you cannot measure it, so eventually it will go 0. For instance, do you hear me? Hi guys. Hello.
Yes, sir.
So your
Am
voice
I
is not
audible?
audible.
Could you
Yes.
respond, please?
Yes, sir.
Now you're audible. The previous
Cool.
time
Thank
you
you.
were not.
Thank you. Thank you. So see some. Yeah, I just saw that there was some internet disruption. That's why I asked again. Okay, so I hope this part is clear because this would be an asymptotic exercise. Eventually, this would goes to 0, but after a long time. Okay, and we now see why this is happening. Why? So we can mathematically see why it is happening. Okay, so let's say you consider a case having uh, so could you see my slide or you're still seeing my board?
Yes, sir.
You can see the slides, right? Perfect. So let's look at a case, a simple case. You have a controller which is marked by C and a process marked by P. Just there are two things. There are assuming all the transfer functions related to final control element, sensor, sorry, let's say sensor, basically I to P, etc. All unity, just for simplicity. Just we are only looking two key variables that we wanted to look on. So C and P, okay, controller and process. And let's assume that let's assume two conditions. One you use P controller, one you use I controller. So in P controller, what would happen? The error would be summation. Sorry, it is proportional to the error, and P would be your controller gain. While in I controller, it is it is basically 1 by tau I times S, right? So let me call this 1 by tau I as Ki. Just for the sake of simplicity. Ki here stands for 1 by tau I, okay? Just to make them in the same comparison. Here there is a Kp here there is a Ki here. You see the transfer function has a denominator S, which essentially indicates the integration or integration. If you recall the process dynamics, when you have integrating systems, you have seen that they have a denominator transfer function. So having just S alone. So now let's compute the error. Okay, the error is equal to R minus Y. Okay, R minus uh, Y of S. What is Y of S? Y of S is this, which is P times U. So P times US. And what is P? P in this case is Kp times E of S. So now you take E of S into the left hand side. What you would really see that E of S, which is the error transfer function. So E of S you take into the right hand side. So it would be 1 by Kp times Ps would be the denominator term. Let's do the same exercise for the I controller. Okay. So it would be R minus Ps. Okay. And your controller is Ki minus S because it is integral. So Ki minus S times E of S. Now again, let's try to isolate the error because we would like to see the error, what is happening, right? So eventually, give me a minute. So this is the original variable plot. I can also make a mirror image plot of error. So I'll just, instead of plotting ym, let me plot error, which is basically ysp minus ym. So over time, and you really need to be, and the set point of error is always 0 because that is what you need, right? And what you would see a similar thing, that initially there may be a high value. So ideally it should be close to this, right? So let me just draw. So this is what you need. So it has to be over here. So you would see that there would be something. And asymptotically, this error should be 0. Initial error cannot be 0. So you can even say it is a very high value. I can even erase this. So just a second. So let me just say error would be slowly. Finally, it should be 0. So this is the expectation. Now coming to, so we are now trying to see how the error profiles look like. So what we have done is we are now calculating the E of S and see E of S, what is the nature of the E of S. So getting the nature of E of S would give we'll get to know what is the nature of E of T, because you just need to take an inverse, right? So now let's check here. So here E of S is 1 by P times Kp, while in the integral case, because of this 1 by S is right here, you would see that E of S is of course R by 1 plus, when you take this guy, this side there will be 1 plus Pk Ki by S. Now let's look at what is the final value. What is that is our aim. So we need to make E of S to be 0. Or rather E of T to be 0, which essentially E of making the overall error to be 0. If you look at the transfer function of E of S, the only way, because P of S is what? Process transfer function. This is fixed. Because when you work in a process, its transfer functions of course fixed. If it is be it a tank system, be it a heater system, be it a reactor. Okay, so whatever be the case, it is fixed, and you can only play with this guy, which is Kp. The only way The only way, so the only way to make the E of S to be 0 is to have Kp to be infinity, which is not a realizable condition. A controller, a proportional controller having gain infinity, because you cannot have an infinite gain, right? But while here, so look at this E of S, and you know what would happen when t is to infinity because of this s, right? You see that by finite value theorem, you would see E of S would tend to 0. So as a result, you can see that mathematically. So we are now proving it mathematically. Why P controller can eliminate the error only if your gain is infinity, while I controller can of course do this without having a high gain. There is nothing is needed, but only thing it is at t is equal to infinity, which is like the final value, which essentially means that it would happen, but like at a very large time. If you are ready to stay till that time, I am okay with that. Okay, so there is also one so there is also see everything would have a pros and cons, right? So integral action, of course, eliminate 0, eliminate offset. Integral action would definitely eliminate offset. From here is, what are we going to lose out of that? Huh? See, you also see this Kc times Pt. I am writing now for Pi, okay? And 1 by tau I times integral of Pt. Sometimes, okay, so you would reach so initial, so let's say you were at a starting point and this was your set point, okay, and you initial error was very high and you reach the set point very fast, and it just keep on oscillating. As a result, so this is positive error, this is error, this is error, this is all, then this is all negligible error. So when you take the integral summation, the error term may be very high. Integral of error term, no? Very, very high. So as a result, what would happen is so the controller would be very, very active, even though there are minimal errors. So here the deviation from the set point is small, but due to this highly accumulated error, because there are, so this is all summation, because eventually there is no way to nullify the positive error with a negative error in this case. And as a result, the overall error, the residual integral term happened to be very, very high amount. So your controller would be very active even if you need to take small correction. So that might bring in a very, very aggressive response. So to remove that, there is something people do known as reset wind up. So this is basically known as wind up, because your controller is just in a very, it's like spring wind up. No, it's a very, very powerful position. Even if you want to do a small change, you release the spring, you will get a punch. So you really don't want that, because it's fully energized. So people would tend to do what is known as resetting the wind up, which essentially means that you would discard this integral action after some time. So this is the overall term. So whenever see, eventually everything would happen. How do you operate your control valve? So your error, everything, you all go to your control valve, and your control valve. Let's say your control valve is fully open. You cannot do anything more than that by a controller. So that's what a controller could do, because you have only one control valve, be it air to open or air to close. It is fully opened or fully closed based on which type of valve it is. further increasing the error, you cannot do anything because your valve is already at the extreme condition. Okay, just to avoid accumulating this excess error at that time, people would drop this particular term. So that is basically known as resetting the winder. So whenever your control valve is in a fully armed position, either it is fully open or fully closed, you just stop the integral action because there is no point in accumulating this error further. Because your customer who is going to eventually go into the field and do opening the valve, which is the control valve, right, has done its full power. What else you could do? Even if you ask him to open more, there's no way. It's already open or either it's already closed. So people would, so in that context, you might kind of consider dropping the integral action when the valve is fully open or fully closed. Depends upon which valve it is. Which is essentially what it says. So reset wind. So this is by temporarily halting the integral action whenever the controller output saturates. And the last one is, so we have seen three terms, P, I, and D. We have seen the first two, and let's look at the last one, which is the D. So derivative action, basically the rate. So derivative stands for the rate, no? So rate of change is an anticipation. So this is the rate of change, which means that this is the way it may operate. So this is the rate in which it's going to operate. So if you need to bring in some level of prophecy or some level of predictiveness into the overall action, so this is the current error profile, and this is the rate of change of error profile, means that this is the way it's going to change. Okay. You can also have a integral term, derivative term into the controller. So P of t, which is controller output, P bar, of course, the bias term, and TD, which is generally known as integral time into DET by dt. And when there is no error, as you would really see, there is no rate of change of error, this term would get dropped, and eventually it would be P bar is equal to PT. So the point, so there is a mild catch here. Okay, so your integral action as you really see is K times dE by dt plus P bar is P of t. This is the derivative term. So we have seen P controller could be used alone, I controller could be used alone, and PA controller could be used as a conjunction by kind of integrating or considering best of the both worlds. But you cannot use derivative alone. Why? Because it is not looking at the error is reaching the set point or what. It just look at the rate of change of error is small. At any point, if the rate of change of error is small, regardless whether it has reached that point or nothing, your derivative actions will get stopped. So let's say if you look at the error profile E versus T, and initially there is a change, and you see at some point the error happened to be a little bit constant, then your integral action is going to be 0. Sorry, derivative action is going to be 0. So it is not what you call fair, or it's not useful to use the integral action, sorry, derivative action alone, because whenever there is a rate of change of error 0, even if it did not reach the set point, this term would be, contributions from this term would be 0. But you can integrate them with P, I, and D, which essentially means that it would also bring in this rate of change of error. So that would eventually result in the celebrated PID form of the controller. So the celebrated PID form of the controller. So your P of t would be P bar plus K times ET, which is the proportional term, and 1 by tau I times integral of ET dt. If you need to put star here for a dummy variable, you can do that. Okay, this is the integral term, and of course you should have a derivative term tau d, dEt by dt. So this is the most commonly used control structure because it contains all trade-offs. If you need an initial pull, SP would give. If you need to do an offset elimination, that I would give. Okay, and if you need to do some get a directional influence due to the rate of change, that derivative part would do. Let me check. Okay, and I will stop here. What's the time? 11 o'clock. So we'll continue from here and we'll complete this part tomorrow. I think we are all close to 11. And we did not have the tutorial yesterday because we could not complete this part. If we complete it tomorrow, we'll have, or maybe Friday, either we could have the tutorial on the Friday or the coming Monday, up to whichever up to your convenience, and coordinators can inform me accordingly. So I don't want to hold you back anymore, and thank you and see you tomorrow. Bye-bye.
Thank you, sir. Sir, there was just one small request that a few students were saying that, there was a negative answer in one of the minor questions. So could you go in there and maybe reevaluate that possible?
Okay, so I can tell. So I have got various emails. So we cannot reevaluate it. I'll tell you why. Because at least a few people emailed me, so saying that I did not put the negative sign in the thing. So there is a difference if you put a negative sign and a positive sign. So if you put a negative sign, your overall system is will not show an inverse response. But if you put a positive sign, it's a right half plane zero. The entire meaning would lost. One is a stable system and one is an unstable system. The negative sign has a very, very profound meaning. If it was just something, I would consider giving it. This is like saying one is tranquility and one is like full chaos. So in this context, I am afraid that I will not be able to. I have got certain emails. I did not respond to any of them. I thought I will just write a common email saying this. Since you asked, I am responding over here. That particular problem, the presence or absence of negative, essentially means that the system is either one is perfect and one is completely imperfect. So in that context, of course, I'm afraid I'll not be able to put that negative marks for just who wrote the magnitude. I hope that clarifies. And if it was just a calculation and it's the magnitude, that's different. But that particular problem, when you talk about a transfer function, that has a very, very important meaning. Got it?
Sure, sir. I'll let people know.
Okay. Thanks a lot,
Thank you.
Ashutosh.
Thank you, sir.
Bye-bye.
Thank you.